All right, so we're going to build on what we talked about last time today. We're going to add another term to these equations and get at competition. So what that means is we're going to be working with some new models. These flow naturally from the model that we developed last time on density-dependent population growth. But we're going to call these ecological Terra models, and I'll tell you about why. So our goals for today are going to be to contrast the definition of intraspecific versus interspecific competition. We're going to use these ecological Terra equations to graphically model population growth of a species in the presence of another species. So we have two species interacting now, not just one population increasing. We're going to do that visually with these phase plane diagrams, and you'll learn what the ZNGI, the ZIGNI is, and we'll talk about equilibrium points. And once we do all this, you'll have the tools necessary to predict the outcome of competition between any two pairs of species based on how they interact, how they relate to each other. So this is what we're going to be doing. You're going to get comfortable using these graphs so you can complete or fill one in an exam question, for example. But it's all going to be based on these population growth models. So let's start with defining these terms so you guys have it, right? Have the vocabulary. Intraspecific competition with an A refers to the competition that happens between members of a single species as their population increases and they start to deplete resources and compete for those limiting resources. Individuals of the same species, and the way we talked about it in class last time is you can think about this competition as the degree to which a species growth or species population feeds back negatively on its own growth, its own population growth. The more individuals of the species there are, the slower that population grows. When we use interspecific, we're talking about between species, between two different species. So competition among individuals of different species that are in some way using the same resources, so those resources are being depleted, and therefore that competition is negatively affecting the growth of both populations. One is affecting one population and the other is affecting the other. Keep in mind that both of these things can happen at the same time. That's why we're going to start with the model of intraspecific competition, the model of density-dependent population growth, and we're going to add to it a term that incorporates the effect of a second species. So that's what we're going to be doing mathematically. Who can remind me what kind of growth is depicted here? Let me see if I can turn the front light off. Yeah, that works, right? What kind of growth is depicted in this model with that kind of stretched out S shape? Like, oh, that's a great example of blank growth. Yeah.
Exponential?
It's not exponential. That was the first one. The exponential is when it goes up like this forever, but when you get that stretched out curve. You want to change your answer?
Yeah, logarithmic.
Logarithmic, you've got the right L, but logarithmic is increasing orders of magnitude. There's a different L word. You remember what it is? Okay, you want to help them out? Logistic growth. Logistic growth is where you're bound by two population sizes, 0 and some maximum population size the environment can sustain. What's another way to describe this pattern? If you don't want to use the word logistic growth, what other kind of population growth is this? Tony, do you know the other term for it? Anybody else? It's the title of the slideshow from last time. It's not growth of the population that's independent of population density. It's instead, yeah?
Density dependent?
Yeah, density dependent. So these are both the same thing. Logistic growth models describes mathematically the pattern you're seeing here, where you've got an upper and a lower bound, and so you get that S curve. But if you think about it ecologically, what you're seeing is that the growth of the population depends on the density of the population. So we call it density-dependent population growth. What sets that maximum population size that the environment can sustain? Or what is that maximum population size that the environment can sustain? Yeah, Paige.
Is that like the carrying capacity, K?
It is the carrying capacity. It's K. It's the special value of N, population size, at which the population is no longer growing. It's maxed out. Okay. This is the model, or this is the mathematical equation that describes the model we just talked about. We're just reviewing it. I want to make sure you guys can read this. Read it as though it's in plain English. Can someone tell me what this dNdt means? Yeah, Paige.
The change in number over its change in time.
Yeah, it's basically the rate at which the population is growing. It's the rate of population growth, or the change in population size per change in time, as that time approaches zero, approaches kind of any one moment. So it's the rate at which they're increasing. It's individuals per unit time. Someone remind me what the little r is. Kate, was that a hand?
No, I'm just writing.
Okay, right. What's little r? We've met little r before, haven't we? Yeah, Claire.
Natural log of 1 plus b minus b.
Nice, yeah. But can you say that in, so that's correct, but can you say that in kind of plain English? Or can you provide the units that r ends up having? It's very similar to the rate of population growth, but there's something extra in there. Yeah.
It's the instantaneous rate of increase.
Yeah, instantaneous rate of increase, and then last time I said there's another way to say that I also want you guys to be familiar with. Paige?
The average rate of increase?
No, not the average. It's the per capita. So instantaneous or per capita, those are, we can use both of those terms. The reason I like using per capita rate of increase right here is because if a growth rate is measured in individuals, say per year, maybe it's a plant that's producing seeds every year. You could have a situation where each plant might produce 20 seeds per plant per year. 20 seeds per plant per year. Now, there could be 100 plants, right? So that's going to be your N value, population size. 100 plants. What cancels out here? Seeds per plant per year times 100 plants. Yeah, plants, right? So then what's your resulting units is seeds per year, right? That's the unit of a population growth rate. What's the growth rate going to be if you have 20 seeds per plant per year and 100 plants? Not 100, there's an extra zero here, right? 2,000 seeds per year. If you had 1,000 plants, right, you'd have 20,000 seeds per year. So this R times the number of plants, this is why it's per capita. This is per capita, then you have some capita, some number of individuals, and that gives you the number of individuals per year. Does that help? Do you guys feel like you know R better now than you did? It's just the growth rate, but it's got that per individual in there as well. Seem okay? Like that. Individuals per individual year times number of individuals gives you that rate of increase. And then, what was this term all about? What is adding everything that's in parentheses there do to the model? If we just had dNdt equals Rn, what kind of model is that? Garrett, do you remember? If you just have dNdt equals Rn, what kind of model is that one?
I don't remember.
That was your exponential growth model. If we ignore this, it's the model we did right before the exam, right? It's exponential growth. And you could just keep increasing n, and d n dt is going to keep going up, 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 up forever. So, Sonia, you were going to tell us what this does to the model?
Oh, it adds the carrying capacity so it can't grow infinitely anymore.
Exactly. It adds in this carrying capacity term such that d n dt won't go up, up, up forever anymore. N is still population size, so what does this all become when n is very close to 0? When n is very small, what will this term converge on? 1. So if n is very small, there's nobody there, your environment, or your, let's use an analogy. Instead of the environment, you're going to a buffet. I used this with a student who came into my office earlier. If you go into a buffet or a big party with a big buffet and you're there early and nobody started eating anything yet, you get to pick all the best food you want, fill your plate, eat all you can, no problem. It feels to you, if it's just you and maybe 3 other people there, it feels the same as if there's no competition at all. Because there's plenty of resources. You're not both trying to get the mac and cheese or whatever you like best. There's plenty of resources to choose from. But as the population size approaches the maximum size that that buffet or that party can handle, what will this become close to? Yes, as n gets close to k. Let's say n gets all the way to k. Let's say n and k are the same.
0.
Becomes 0, right? Say you could support 10,000 people at your grand party. It's a big party, I guess. If there's 10,000 people there, they're going to eat all the food that you planned for. So your carrying capacity just goes to 0. If you have some population size, 10,000 people, and some growth rate that's greater than 1, let's say r of 2 or something greater than 1, this is going to be a big number, right? 10,000 times 2 is 20,000, but you're multiplying that by 0. So what happens to the rate of growth? Is 0. The population is not going to grow anymore. There's no more resources for anyone to take up. So what that means is that you end up with a situation like this. If we just had the exponential model over here, it'll keep going up and up and up as long as the population size keeps increasing over time, the rate at which it's growing, the steepness of this line is going to keep going up, up, up. But then once you add in density dependence, once you add in the effect of competition, the curve is going to start out looking very much like the exponential curve. A little bit lower, a little bit depressed. There's a little bit of space between these 2 lines. But then, as time goes by, as population size increases, the difference between these 2 models is going to increase as n approaches k. Eventually, this one's going to level off, whereas your exponential model would have gone on. Do you feel like that was a useful review? Does it seem okay? All right. So now what we're going to do is take this model and we've got the effect of this species negatively affecting its own growth rate. We want to say, well, what happens if you have 2 species in the same environment, they're interacting, they're competing for the same resources? Well, we're going to need 2 growth models, one for each species. So what have I added to make this 2 different species? What have I added to the equations?
Subscripts?
Yeah, subscripts, right? So this is our model for species 1, and this is our model for species 2. Without interacting yet, it's just 2 models. Just 2 different models of population growth that have intra-specific competition. They're limiting their own growth. But what was interspecific competition? How could you define interspecific competition?
2 different species competing.
2 different species competing, but can you frame it in terms of growth limitation? could you say that same thing? It's correct, but how can you say the same thing in terms of growth limitation? This species is limiting its own growth right now. But there's nothing mathematically that's causing this species to limit that one's growth, right? Emma, did you want to take a stab at it?
No.
Okay. A question then?
I was gonna say that that one was limiting the other one's growth because if it's taking other resources, but then you said there was nothing
Nope.
mathematically.
Not yet. I haven't written anything yet, but your answer is exactly correct. So interspecific competition is the degree to which one species limits the growth of another. So let's add that in. Adding that in can be traced back to two scientists who were working at about the same time on this problem of species interactions and modeling that mathematically to make predictions about the outcome of competition. Let's see, what's his first name? Blanking on his first name. Lotko was a chemist, so he was used to thinking about densities of things and interactions of chemicals and stuff, but he was interested in biological systems and wanted to apply that training to biology. Meanwhile, at about the same time, Guido Volterra was working in Italy, originally a mathematician, and he became interested in applying his mathematical training to biological systems, to species interactions. So at roughly the same time, they came to very similar models, and so we attribute these models to both of them. They didn't just do it for competition, they also did it for other species interactions, but we're going to focus just on competition for now. Before I show you the models, since Emma correctly said that interspecific competition is the degree to which two species limit each other's growth, can you guys think of any other species interactions? Pairwise species interactions. Any other ways, any other terms that refer to how two species might interact? Yeah.
Parasitism?
Yeah, parasitism is a good one. Who benefits and who loses in parasitism?
The parasite benefits?
Yeah. And the host, is the host benefited or negatively affected nurse's fitness maybe?
Negatively.
Yeah, right? You got a parasite, you gotta feed that thing instead of feeding your, putting that energy into feeding your own young. That might affect your interaction. What's another way two species might interact?
Codependent?
Explain a little bit.
Like where they both help each other?
Yeah, where they both help each other. So, in the textbooks, that kind of relationship is usually called a mutualism. And you said they both help each other. You guys think of any others?
Communalism?
There's an S in there. Can you explain?
There's like one benefits and one doesn't really like benefit or is negatively affected. or
Yeah.
something.
No real difference, right? That is, yeah, commensal. You're just missing that S. Yeah. What's another common one? The one we're gonna talk about. We're doing competition now. At the end of the year, we're gonna talk about the last one. Could go up here. You're gonna think it's so obvious.
Predation?
Yeah, predation. Here. Predation is a little bit different than parasitism because in the case of parasitism, parasite wants the host to stay alive so they continue to parasitize. Whereas in predation, you're dealing with one individual loses, well, its fitness is drastically reduced, right, upon death. What's the kind of interaction here for competition? How would I'm using these little plus and minus signs for positive effect and negative effect on fitness or population growth. What signs should I put there for competition?
Negative.
Yeah, Just what Emma said, each species is limiting the growth of the other. Good. Now let's see what that looks like. Here. Remember the parenthetical portion of the equation was just to limit, was just kind of a multiplier that limits population growth rate. Now we've added into the model for species 1's growth the negative effect of species 2. And here for species 2, we've added into that the negative effect of species 1. Now you'll notice I didn't just add n2 and n1 here, I also have these new coefficients, alpha and beta. So alpha and beta are coefficients of interspecific competition. Now they're relative. What I mean by that is they quantify the effect of adding an individual species 2 relative to the effect of adding an individual species 1. So if you have a population and it increases by one individual, competition among those individuals got a little stronger, right, with just one more individual. If you add an individual species 2, it's also going to increase competition just a little bit. But are they going to interact in exactly the same way? Do you use exactly the same resources in your home as your dog? Or do you guys maybe share some table scraps, but the dog gets most of its energy and its food from another source, not a source that you're using? I see some heads nodding, right? You see what I'm getting at here? Like you and your dog might share a little bit of food if your dad's feeding him off the table scraps or whatever. But for the most part, the house can support you and your dogs because the dogs are eating one set of food and you and your family are eating another set of food. So the resources are separated. In nature, is a raccoon and a possum, are they going to eat exactly the same resources? Pretty close, but not exactly the same, right? There's all these memes going around about how possums are so great because they eat ticks. Raccoons aren't eating much of ticks. They're going to their dumpster and getting their full that way, right? So species don't, adding an individual of one species is going to negatively affect its own growth. Adding an individual of another species is also going to affect the growth of species 1 because it's using resources, but maybe not exactly the same because they're not the same species, so they do different things. Maybe you're not worried about food, maybe you're worried about nesting sites. Do all birds nest in the same places? Yeah, you might see a robin in a tree, but then your parking garage has all kinds of barn swallows, so they're not using the same places to build their nests. So let's take these one at a time. I know there's 2, so it feels like a lot to keep track of. So let's take these models one at a time. We'll just think about species 1. So this alpha term basically comes down to these 2 points. If the second species consumes resources at a higher rate than species 1, then this alpha value is going to be greater than 1. The effect of an individual species 2 is going to be really strong, negatively affecting growth of species 1, because you're multiplying this one individual times something greater than 1, 1.2. If you've got a big animal and a small animal and they're competing, imagine, what's a good example here? We've got, say you've got, what's a good example here? 2 species of birds, right? And they both eat seeds, grass seeds in the prairie or something like that. The big one needs a lot more seeds than the small one, and it's probably pretty good at finding them. So if you just have a few of those, they're going to be equivalent to just one, they're going to be equivalent to many little birds. So a bigger bodied individual might take up more resources. But if species 2 consumes resources at a lower rate than species 1, or consumes only some of the resources that species 1 needs, then it's not going to have a big effect. So alpha is going to be less than 1. There's still going to be an effect because there are lots of species coexisting, but maybe not as big effect as if they were individuals of the same species. which do you think is more likely in nature? Do you think that one species is going to be consistently better at accessing the resources that another species needs all the time? Or do you think that species tend to have some shared needs, but not all shared needs? Do you think that if you have any two species that might compete, do you think that adding an individual of one might have a really strong negative effect on the growth of the other species? Or do you think that their species aren't equivalent, they use some different resources, and so maybe they're going to be slightly less, it's going to negatively affect one, but not super severely? Which one seems more reasonable? Yeah, the second option, right? So that's because if we think back to the term ecological niche, which we introduced once, and you're going to be thinking about ecological niches again when we talk about adaptive radiations next time. You think about the needs of a species. The ecological niche is the range of physical and environmental conditions that a species needs to survive and reproduce, and the array or the range of necessary resources, the kinds of food, the kinds of, the way they access water, and other kind of limiting resources. This other term, niche differentiation, that you'll be thinking about when you read about your adaptive radiations, refers to the way in which two competing species use the environment and available resources in different ways. So if you have niche differentiation, they're not going to be using the resource in exactly the same way. If we go back to our party and buffet analogy, if you go in to a restaurant, or let's say a buffet, and they got this stuff out there, right? And you and your friends like the exact same stuff. You're both going for that mac and cheese, and there's only a little bit left. You're going to be competing really strongly for what's left there. You have to play rock, paper, scissors to see who gets it or something. But if you're all about getting the mac and cheese with your barbecue, and your friend's all about getting the coleslaw with your barbecue, no problem. Each goes to the separate area, and you've differentiated that niche of what sides you want with your barbecue. Seem okay? So now let's start actually playing with the equation a little bit. Without this species 2, what value of species 1, what population of species 1 rendered the rate of growth 0? What value of n renders this rate of increase 0? 0 will do, 0 won't do it, right? Remember, this k is going to be some positive number. Minus 0, that's going to be k over k, that's 1. So what value of n is going to render dn dt 0? K. K, right? So now let's, what value of alpha n2 could render dn dt 0? If you imagine n is now 0, there's none there, so they're not limiting their own growth at all. As soon as you get one individual species one in there, that population is going to start going up. But what value of alpha n2 could render this 0? K minus 0 minus k again. So any combination of n1 and alpha n2 that sums to k will render this 0. Keep that in the back of your mind. Yeah, keep that in the back of your mind. And we're going to solve for equilibrium. We're going to solve for 2 cases of equilibrium. Anyone tell me before we jump into that, what do I mean by equilibrium here, probably? What's equilibrium mean generally in your mind?
It's like a constant equal rate.
A constant, not necessarily a rate, but it could be a rate, but something that has become constant, something that's settled down and is no longer changing. It could be a rate. It could be a population size. In this case, we're talking about a growth rate. So this is no longer positive or negative, it's 0, then the system is at equilibrium. So we're going to solve this when we set dn dt equal to 0. One way that you can do that is, as you guys were saying, having n1 equal to k and n2 equal to 0. How could you figure out the value of n2? How could you solve for n2 such that the rate of increase is 0? Let me write it over here. I want you guys to take a moment and see if you can take a stab at solving for n2. And I'll write it up here to get you started. We want to solve for n2. You guys want to do it together like we did last time?
Yeah.
Yeah? What can we first do to get rid of, to get n2 by itself? What can we multiply both sides by? Or divide both sides by? You could do n1, yep. We could do more than just n1 though. That's not wrong. It's just taking it really slow. Once, if you were going to divide both sides by n1, what then else would you also divide both sides by? Yeah, r1. We can actually do that together. So let's multiply both sides by 1 over rn. That's the same as dividing both sides by rn. Seem okay? So what does this look like now? That becomes 0, right? And now we've just got this competition term we were dealing with. What would we do next? Multiply both sides by. Everyone okay with that? Seem reasonable thing to do? Multiply both sides by k1. What do you get when you do that? 0 equals just that numerator, right? What do you think, Sam? Can you get us to the next step?
No, I'm sure.
We're going to get that n2 by itself.
Yeah, for sure. Nah, I'm not your guy today. Sorry. I'm sure there's simple algebra, but I have no idea.
It's a whole bunch of minus signs.
Yes.
So what would you probably do?
Well, I'd probably add some.
Yeah, you probably add
I do.
All right, Sam set it up. Who wants to, to dunk it?
Lily. I think Lily wants to help. Lily, what do you want to add?
No.
Alright, I feel
What are
better.
we trying to get back to?
I'm sorry, very hard.
Will you add the 8 and 2 over?
Yeah, you can just add this.
Yeah.
To this.
Oh, dude,
There we
I thought that's what we were keeping there, so I was like, I don't.
Well, yeah, you could keep it there, but then you got to do a bunch of other things first.
Yeah, nah, sorry.
Alpha n2 equals k1 minus n1. What did I say the value for n1 is going to be in this case?
Okay.
Okay.
0. In this case, it was going to be 0, right? Because we're going to solve for the largest population size of species 2. It's going to render the growth of species 1 0. So this one actually goes away quite easily. It's 0.
How do you know that?
Because when I set it up, I wanted you guys to solve for the value of n2 when n1 is 0.
Gotcha.
So we could have gotten rid of that in the first place, then you just would divide both sides by r. Maybe that would have been a little quicker. So if this is 0, kn minus 0 is going to be just k1, right? So now what do we do to get n2 by itself? Exactly. Divide by.
Wait, so how did you get rid of minus n1?
Because n1 is 0 in this case.
Okay.
We're solving for the population size of species 2 when n1 has gone extinct. zero population. So, I told you, or we talked about how there's a whole bunch of combinations for species 1 and species 2, such that there's a population size here and here, where together n1 and alpha n2 equal k, such that k minus k is 0, and this whole thing goes to 0. One of those situations is when n2 is 0 and n1 is k. The other one that you just figured out is when the value of n2 is the carrying capacity of species 1 divided by alpha, which is that coefficient of competition, which can be species specific. It depends on which pair of species you're dealing with. It's something you would measure empirically as a researcher or an ecologist. You would find out what that degree of overlap is, how much they share resources. Okay, so we just did this. Solve for n1 assuming n2 is 0, solve for n2 assuming n1 is 0. And now we're going to look at a phase plane diagram. I'm missing a slide here. So let's think about these axes. This is really important. When you have a test or a question on the exam, the first thing you're going to want to do when you see one of these is make sure you understand the axes. That's what trips people up every year. This axis here represents the range of possible population sizes for species 1. This axis represents the range of possible population sizes for species 2. So if you ignore the black line for a moment, what does this point mean in this phase plane diagram where the axes are population sizes of 2 species? What does this point mean right here? Say it a little louder.
There's nobody. There's no
Or very small, right? So a very small population size of species 2 on this axis, that's your y value, and a very small population size of species 1, that's your x value. So this point defined by xy is 10 individual species 1 and 10 individuals of species 2. If species 1 grows in population size and species 2 does not, which way should I move my finger? If species 1 increases in population size and species 2 does not.
right.
So right.
Yeah, good. Now we're out here. Now let's make species 2 grow, and we'll keep species 1 constant.
Up.
All right, now let's bring both species populations down at the same time. Be able to navigate like that on this phase plane. Now, what's this line? Well, we solved for the population size. What happens when n1 equals k1? What's happening to that population at that point?
It's staying the same.
It's staying the same. What happens when all of the individual species 1 have gone extinct and your population size species 2 is way up here? What's happening to the population of species 1?
Species 1 went down.
Yeah, all the way to 0. Exactly. It's extinct. What does this line represent then? All possible combinations of species 2 and species 1 that result in what?
The threshold,
A threshold. Can you explain a little more?
like the most that can be of both at the same time.
We're still just thinking about species 1, but you're real close. You're right there. Sonia, you want to add to that?
I was gonna say the line is when the rate of change is 0.
For who? We're only thinking about 1 and 2 species right now. Oh, the rate of change of who? Species 1. So this line represents all the combinations of these 2 terms that will sum to k and make this 0. Right? This line represents all the places, all the combinations of the two populations that will result in zero growth, zero net change for species 1. So we call it the zero net growth isocline, or the zigny. And that's when the rate of increase for species 1 is 0. That could be when all of species 2 are extinct and species 1 is at its carrying capacity. Or it could be somewhere here where there's some of species 1 and some of species 2, but they've eaten all the resources up. And species 1 is maintaining, but it's not increasing or decreasing. So if I'm right here, where there's a little bit of species 2 or a little bit of species 1, what's going to happen to species 1's population? How's it going to change if you just set up a scenario where you have a small population of both? What's going to happen to species 1? It's going to increase. So which direction do I have to move my finger to show that?
Right.
Towards this limit, which is no longer carrying capacity. It's a little bit less than carrying capacity, but that's because there are some individuals of species 2 in the environment that have already taken up some of the resources. Yeah.
Oh, so will there ever be like a point on the line that says which one, or am I?
Well, every point on this line is a population value of species 1 and a population value of species 2 that results in there being not enough resources for species 1 to increase anymore. So here's how species 1 is affected on this phase pointing diagram. If its population is to the left of the line, it's going to increase towards the line. And if its population size is above the line over here, it's going to decrease towards the line. What changed? I'm going to go back and ask you what changed. Go. I forgot to change the title of the slide. Let's fix that. Now we're thinking about a different isocline for species 2. Yeah?
I was gonna say, now we're talking about when the rate of change for species 2 is so zero.
Well stated. When the this is the line, the zigny, that represents when the rate of change for species 2 is 0. So if species 1 is extinct, species 2 can reach its own carrying capacity, K2. If species 2 goes extinct, then species 1 can increase all the way up to this value, whatever it is. It depends on the strength of competition between the two, that beta value. So if you're thinking about species 2, you have to move the finger up and down the y-axis. If you're speaking about species 1, you got to go left to right. So let's explore these relationships. You know what? I want to make sure we can do a diagram. Yeah, this is good. Okay. So let's think for a moment about how the population size of species 2 is going to be related to species, or is going to limit species 1. So if you've got a reasonably high value of K, what does that tell you about the strength of intraspecific competition for species 1, if it's got a high K? Is that going to be strong interspecific competition or weak intraspecific competition, just for species 1? Weak. If K is high, then within species competition is low. But if the strength of interspecific competition is reasonably high, it approaches 1, what's that going to do to this N2 value? What are you going to get if you divide 200 by some decimal here? You're going to get a larger number, right? What if the strength of intraspecific competition is high, such that the carrying capacity is low, and we keep that interspecific competition coefficient the same? What kind of value for N2 are you going to get now? what you get when you divided 200 by 0.5. You got 400, right? So a lot of individuals of species 2 were necessary to suppress species 1. But if you divide 50 by 0.5, what do you get? 100. You still need a lot of species, a lot of individuals of species 1 relative to species, or species 2 relative to species 1. But because species 1 is already limited, there's already a low carrying capacity, it doesn't take as much. Instead of 400, it only took 100. What if the strength of interspecific competition is really high? What if one species uses almost exactly the same resources as the first species? How many individuals of species 2 is it going to take to suppress species 1 to extinction? 100, right? The same number of species 1 are going to negatively affect species 2 as species 1 would itself. And what if actually they're not using many of the same resources at all? There's maybe like one food item they both share, but they're all eating lots of other stuff too. What's it going to take? How many individual species 2 is going to take to suppress species 1 or hold it at 0 growth if they're at very low competition? What do you get if you plug that in here? 1,000, right? If they're not interacting much at all, it's going to take a lot to suck up that little bit of overlap and use all those resources such that species 1 can't grow anymore. Let's look at it graphically. It's a little easier graphically, and I think that'll be it for today. So, competition. I like to think about it in terms of plants competing for something like soil nutrients or water or maybe light if it's limiting and you're in a forest understory. But let's think about it with some herbivores. We're on the Serengeti. What are our 2 species that are interacting here that are competing for plant resources? Zebras. Anyone recognize the other one? I think those are wildebeest, but you're in the back. I don't know why all right. Yeah, these are wildebeest. Oh, are wildebeest buffalo, you asked?
Yeah.
I don't think so. They're a different genus.
I'll look it up.
All right, good. Okay, let's do this. Let's say that we have a situation where equals, let's say, 0.4, and K2 equals 12,000. So these 2 species both have rather large carrying capacities in this scenario, 10,000 and 12,000. These are our zebra and our wildebeest. You can have big herds, right? And they're using a lot of the same grasses. Maybe they don't eat the same ratio of grasses to herbs and things like that. So it's not a one-to-one here for these constants. They're using different resources. So we can set the degree to which species 2 affects species 1 at 0.4, and the degree to which species 1 affects species 2 at 0.6. So let's do our first one here, species 1. We're going to plot our carrying capacity right about here, 10,000. You remember what value of species 2 is going to drive species 1 to extinction? What's the other end of this geometric Isaac line going to be? Yeah. It's on the board right over there, right? That's how much people look at it. Yeah. 10,000 divided by 0.4 is going to give us what? Is that right? 40,000? So everyone check it. 10,000 divided by 0.4.
25,000.
Yeah, 25,000. So let's say that's about 10 there, so we'll put it up here. 25,000. So now we can put our zero net growth isocline. Like that.
Nice. Good.
Right, now what about our second species, species 2?
That's like 20.
What's its carrying capacity? Carrying capacity for species 2 is 12,000. Where do I put that point on this graph?
On the y-axis.
On the y-axis and a little bit above the 10. Good. 12,000. Where's the other end of its isocline going to be?
20,000.
Yeah, 12,000 divided by 0.6. That's going to come out way out here to 20,000. Let's connect them. Now we've got an intersecting. So now the fun stuff happens. Okay, we're going to start out both populations down here. How is species 1 going to change? Is its population going to increase, decrease, or stay the same? It's going to increase. Which direction do I draw the arrow to show species 1 changing?
Towards the right.
Yeah. What's happening to species 2 at the same time?
Then decreasing.
Where's its carrying capacity? It's up here, right? So what can species do? Species 2 do? It can increase in population size as well. What if I started a new park and I'm stocking a lake with some bass and walleye or something, and I overstock the lake? What's going to happen to species 1 here? There's too many. It's going to go down. Species 1 is going to go down in population size. I've also made way too many individuals of species 2, so what's going to happen to its population size? It's going to go down. It's going to go towards its own zero net growth isocline. Then we can combine these two vectors, and we get this kind of intermediate direction. What happens out in this corner here? What's happening to species 1 here? There's too many. It's past the zero net growth isocline. But what's happening to species 2? It's still below its own zero net growth isocline. So it can go up. So then the combination points you towards the middle. Last one, what's happening to species 1 in blue over here? Which way can its, or is its population going up, down, or staying the same? It can go up, it can go towards its own, it can go towards its own dignity. Meanwhile, species 2, way too many of them, can go down. So in this scenario, when you've got 2 species, and they're overlapping somewhat, but not perfectly, they can partition the resources such that they coexist at these population sizes, both of which are below their own carrying capacities. But nonetheless, they can persist indefinitely at these new decreased population sizes because they're each using some shared resources. All right. Do we have time for the last one? Not really. Let's see. Well, I'll tell you what. I want you guys to try to draw a phase plane diagram like this. But we're going to set these alpha and beta values to something that's not very realistic, but is theoretically possible. Okay, try it using these values, where alpha is 1.2 and beta is 1.5. See what your phase plane diagram looks like using these values. We're going to make the effect of each one on the other really strong, greater than 1. I want you to draw this diagram and put in these arrow combinations. They're going to be a little bit different than what's drawn up here. They're going to be a little bit different than what's drawn up here. And I'll use just a few minutes on Friday before we do our adaptive radiations to talk about what this looks like. If you look ahead in the slides, you'll get hints and help. The other thing that we could do is make the strength of intraspecific competition a lot stronger for one of them. So we could bring one of these down to like 5,000. And then the intraspecific competition is very different for the two. So there's actually 4 possible scenarios. We talked about one. I want you to think about this one, and then we'll talk about the last 2 in class at the beginning on Friday. That's it. I will see you guys on Friday. Right? No labs tomorrow.